Welcome friends, welcome to this course on combustion in air breathing aero engines. My name is Dr. Shwetaprabha Choudhury. I am a faculty member at the Department of Aerospace Engineering, Indian University of Science, and in this course I will be assisted by two teaching assistants who have helped in preparing this PowerPoint slides, and they are Mr. Harsha Uranakar and Mr. Himanshu Dave. They are my PhD students. So, in this course, first we will talk about in this thing we will talk about the motivation that first what is combustion, why do we need to study it, why is it indispensable for air breathing aero engines, aerospace engines and those things, and then we will provide you about the outline of this course, how we are going to study different things. The basic approach will be to start with fundamental processes and then go into more complex situations and then go into engines. But first in this thing as it shows this slide, we will talk about what is combustion. As you see, combustion is the study of chemically reacting flows with highly exothermic temperature sensitive reactions. Okay, now combustion can happen in different forms. It can be something like an auto ignition, it can happen through different kind of flames, it can happen through detonations and explosions. But our primary, our experience tells that what we encounter in daily life is we can encounter a laminar Bunsen flame, what you might have seen in your chemistry lab, which you can see here. This is the laminar Bunsen flame that you see. This is essentially the flame structure, or you can see sometimes a turbulent jet flame in the laboratory where combustion happens in a turbulent flow and the structure of the flame is highly distorted and the flame structure is wrinkled and so on and so forth. Okay. So, these are the first two kinds of flames that we can encounter commonly. Now, what is most fascinating about combustion is that there are two things. First of all, it is a multi-physics, it involves different branches of science. The two pillars of combustion that is involved is essentially chemical kinetics and fluid mechanics. Of course, it also involves thermodynamics, it involves heat transfer, but the two pillars of combustion is essentially chemical kinetics and fluid mechanics, and to develop a great deal of expertise in combustion, you need to understand chemical kinetics and fluid mechanics both in equal details. Okay. The second important thing is that combustion is a multi-scale science. What do you mean by multi-scale will be apparent in the next slide, but you see here combustion is essentially something you have got reactants, then you apply some kind of a spark, and the reactants, which can be like hydrocarbons, etc., it goes to form products which can be carbon dioxide and water. This is our common perception of what combustion is. Now, this is what we see on a global scale. On a broad scale, we see that hydrocarbons like kerosene or methane or natural gas, etc., becomes carbon dioxide and water. But essentially what it involves is that it involves electronic orbital rearrangements at the molecular level. Okay. So, that is why it involves this electronic structure change. Okay. You can see soot formation. Okay. Now, soot formation happens at very small scales. Soot formation happens in a candle flame. Okay. It can happen in a diesel engine. Okay. So, that involves nanoscale processes, whereas it can also involve turbulent fuel air mixing, which happens at a larger scale. Okay. So, it is this different physical processes and different which happens at a different scales of length and time that makes the study of combustion fascinating. Okay. And of course, this is what I was talking about, that it involves different kind of time scales and length scales. So, the electronic rearrangement is governed by the principles of quantum mechanics. Okay. So, that happens at the order of picoseconds and at the order of picometers. Okay. Molecular dynamics, which is a study of different how large number of atoms and molecules interact among themselves, that basically governs is basically when you go from single molecules to multiple molecules and multiple atoms, those scales are of this order. Okay. Then you come to the kinetics models, okay, which are of the order of where the time constant of different reactions are of the order of microseconds and micrometers. Now then you come into fuel air mixing and then the subsequent combustion reactions, and those are essentially governed by these kinds of techniques which we might have heard, and like direct numerical simulations, etc. But those are not involved right now, those are not will be invoked right now. But what I want to give, the basic impression that I want to give through this slide is that once again that combustion is a science, and of course that science is used in heavily in engineering, and that these things involved processes that happens at different scales of length and time, all the way from picometers to millimeters to meters, because an engine is of the order of a meter, whereas in time scale it happens from the order of like picoseconds to the order of milliseconds. Okay. Now why should we learn combustion? Yes, of course it is a fascinating branch of science and engineering, but more importantly it is its role in shaping modern civilization cannot be overemphasized. Today if you see 85% of the world's energy needs is supported by combustion of fossil fuels or biofuels. Okay. Now of course that is huge, right, 85%, and that is even after taking into account all the development in renewables. But then of course since 85% of the world's energy need is supported by combustion, it has led to many benefits. It has made our life smoother. We can go from one place to another at a faster in a very short amount of time. But then that also comes with a price. The price is that of energy sustainability, that is these kinds of fuels that we burn, these fossil fuels, their supply is not infinite. Energy security, we have to get these fossil fuels from some other places, from some other countries. And then most importantly, which has become paramount, become of paramount importance nowadays, is that climate change, because an obvious product of combustion is carbon dioxide, and as you know that carbon dioxide and water vapor both are very strong greenhouse gases. So then but all these things does not mean that combustion itself is bad. Combustion is very important. It will remain important in the foreseeable future, but as for us, that is the present generation and the future generation combustion scientists, the onus is on us to make this process more efficient, less emitting, and more cleaner and more greener. Okay. So that is the challenge of the combustion scientists. How can we optimize this process towards a better future? Okay. And also you must understand that the energy infrastructure is also changing. Okay. Now for example here we are encountering now modern fuels are becoming more and more heavier, in the sense that they are involve very large molecules of hydrocarbons, coal, shale oil, tar sand, etc. And renewable fuels are becoming very important, biofuels, syngas, biofuels, alcohols, etc. And new engines are being devised. Okay. So, so we have to, for present and future combustion scientists, we have to design, we have to get this kind of new fuels, and we have to ensure that those burn properly and in new kind of engines which are more efficient, which are more clean, and which can produce more power in as you might demand for an aero engine. Okay. So one of these hallmarks of this combustion science is the new this TAPS combustor, this 2-in-annular premix combustor that GE has got recently. These new combustors support the Boeing 787 in most cases, and as you see that this involves a lot of understanding of the fundamental understanding of combustion science. This engine has evolved where new understanding of combustion science has played a major role in its development. So the next question is that for aero propulsion, which is the main focus of this this course, that is here the name of the course is combustion in air breathing aero engines. So why is it so indispensable for aero propulsion, and more indispensable in the sense that It's in the sense that it is even in the next 50 years, we do not see that for long distance flights or for military propulsion, we do not see any alternative other than aero propulsion, other than combustion. Now, why is that so? The answer lies in the energy density, the gravimetric and the volumetric energy density. Basically, these numbers, what you see here is that megajoules per kg and megajoules per liter, and on the left hand side in this table I have the fuel type. So, you see that for a lithium ion battery, it is about 0.3 megajoules per kg, the gravimetric energy density, and the volumetric energy density is also 0.3 megajoules per liter. Okay. However, and you can see the other numbers, whereas you see for kerosene, which is the fuel of which is the fuel of choice in modern engines, like modern gas turbine engines runs on essentially different variants of kerosene. You see the same number, you see the same parameter, that is this gravimetric energy density is 100 times greater than 100 times larger than that of the lithium ion battery. Okay. So, why is this number so important? Because in an aero propulsion engine, you can only carry some amount of mass as your fuel, and you only have some amount of a fixed volume in space which will allow you to carry the fuel. So, in that given volume, you are trying to optimize, you are trying to carry many things. So, you cannot have infinite amount of space or infinite amount of load carrying capacity which can be filled with the fuel. So, in a given amount of space and for a given amount of mass, you get the maximum amount of energy out for kerosene, and that is 100 times, more than 100 times larger than that of the modern batteries. So, this is a very large gap which needs to be covered if propulsion has to become electric. So, that is why there is we do not see such chance in the foreseeable future, and hence aero propulsion, as people say, even in this very recent paper that you see, that aero propulsion is most likely to depend on combustion in the foreseeable future. Okay. And that the reason is that, to summarize, it is basically due to the gravimetric and the volumetric energy densities of the liquid fuels. Okay. And also with other things that you see that natural gas has 45, but its volumetric energy density is less. So, for hydrogen it has got very high gravimetric energy density, but its volumetric energy density is very, very less. So, as an engineer, if you are supposed to optimize in this table, you are given these kinds of fuel sources, if you are supposed to optimize, no wonder we will come up on kerosene, and no wonder this has emerged as the fuel of choice in modern aero engines, right. So, this is why because of the energy density of liquid fuels like kerosene, combustion is the main method by which chemical to thermal and then to mechanical energy transfer is implemented in aero propulsion. So, where do we see combustion in aero propulsion? Not only aero propulsion in engines, how does combustion look like in these engines? So, this is the picture that motivates. This is in an SI engine, this picture. This is in a gas turbine engine. This is in an afterburner of a gas turbine engine. This is also an afterburner. This is a rocket engine, and this is a wildfire, and this is a supernova. Okay. So, in nature you see, or nature and engineering, you see combustion not happening in a very smooth and quiescent and a very laminar manner that you see in a Bunsen flame. Rather, it happens in a very distorted and convoluted structure because the embedded flow in which combustion happens is invariably turbulent. So, essentially it can be safely said that all these aero propulsion engines that you see, these gas turbine engines, afterburners, rockets, scramjets, etc., all this involve combustion in turbulent flows, and the combustion is essentially turbulent in these things. The reason is that also all these aero engines are work at high pressure. That the reason comes from thermodynamics, that you must extract work only after you have inputted heat at high pressure. So, at high pressure your density is high, your Reynolds number is high, and as a result of which your flow is invariably turbulent, and you can get you can only have turbulent combustion in these aero engines. And this is how, if you look into the fundamental manner how turbulent combustion looks like, it happens through this kinds of different where the flow disturbs the flame at a different scales, and this is how the turbulent combustion looks like. But then as at this moment, as you see that this process is complex. Okay, there is you have a fuel that is undergoing reactions, then you release energy, okay, and then that releases heat, and all this happens in a very complex turbulent flow. So this means that at this moment we are not prepared to right now understand how exactly combustion happens in the aero engines. So we have to take a step back and understand the very fundamentals of combustion. Okay, if you take a small unit of the flame, okay, or say for example this part, we have to know, or this kind of, if you take this unit flames, if you can, from these different parts of the combustor, and so the road that we will follow is that we will try to understand how does this thing, when you remove the complexities of the flow etc., how does combustion happen in a very simple environment, or in other words in a laminar environment, and even preceding that, what is the basic thermodynamic mechanisms through which or the kinetic mechanisms through which a reactant goes into goes from to become products and releasing energy. So that is what we will first try to understand, and once we have developed enough understanding of simple cases, that is simple flames, simple processes, simple reactions, then we will be in a position to understand combustion in turbulent flows. And once we have understood combustion in turbulent flows, we will be in a position to understand how this how combustion happens in these kinds of engines. Okay. So with that, we have designed the course content. So the prerequisites are pretty basic for this course. The prerequisites are basic thermodynamics, fluid mechanics and heat transfer, and these are the textbooks we will follow. We will heavily depend on this textbook in particular for the materials by combustion physics by C.K. Law. We will also for turbulent combustion we will go into Norbert Peters's book. For gas turbine combustion we will go into Lefebvre's book, Leuwen's book. Scramjets will go into Corinne Segel's book. Okay. So here is the outline of the course. Okay. The outline of the course is that we have divided this course into essentially 4 parts. The part A consists of background materials on thermodynamics, chemistry and transport. So this module 1 will talk about the introduction, which we have just covered. That is why we should learn combustion, why is combustion indispensable in aero propulsion engines, okay, how does combustion look like in actual engines, and how we will proceed from here. So that is covered in this introduction, and then we will cover in the following we will cover chemical thermodynamics, and here we will talk about chemical equilibrium, we will talk about energy conservation, and then we will, using energy conservation, we will arrive at adiabatic, the concept of adiabatic flame temperature. Now this is very important in terms of combustion engineering, this concepts of chemical thermodynamics. Second, this module 2 will go into chemical kinetics. This will tell us how reactants, that is a hydrocarbon fuel, what are the steps and what are the processes through which the fundamental processes through which it can become a product. Okay. And for that we will need to understand the theories of the reaction rates and the different mechanisms. How does it happen? That is covered in module 3 through this oxidation mechanisms of fuels and transport phenomena. So we will understand how hydrogen is oxidized, how CO is carbon monoxide is oxidized, how methane is oxidized, because these are the very basic fuels. Then we will understand how pollutant chemistry works, how NOx, oxides of nitrogen is formed, and how does one develop reaction mechanisms to describe these processes. Then we will understand transport phenomena. By transport we mean like processes like diffusion, processes like conduction and momentum transfer which happens through viscosity. Then we will go into governing equations. Okay. Now, we see that combustion happens in fluid mechanics, and also there is something called chemical kinetics is important. So, how can we marry these two things? How can fluid mechanics and how can conservation equations can be integrated with the chemical kinetics, and which will give us the governing equations with which we can study the different kind of flames and combustion processes. And for that we will go into Reynolds transport theorem to do the control volume derivation. Then we will do the conserved scalar formulation and these kinds of different formulations for the which is typical for flames, for understanding flames. So, in the fundamental processes also we will study about non-premix flame, like a chambered flame we will understand droplet gasification and droplet combustion. Then we will talk about laminar premix flames, the thermodynamics of laminar premix flames, which is given by this Rankine-Hugoniot relations. We will cover laminar flame speeds, and then we will go into the chemical structure of laminar flames. And then we will go into premix flames and limit phenomena, the thermal explosion concepts, S-curve concepts, extinction, flammability and flame stabilization. And then we will finish fundamental processes with aerodynamics of flames, aerodynamic stretch and non-equidiffusion. Now, these things, these fundamental processes, as I said, that in an engine combustion happens in a very complex manner, it happens in a very complex turbulent flows. So, to understand them we have to understand how a small unit of those of the combustion processes that happens in the engine, how that looks like, how we can understand them using this different formulations, and what are the different processes that are involved. So, these parts will cover this fundamental process will cover that. Now, after we have understood these things, we will be in a situation to go to this mechanics and modeling of turbulent combustion, and these parts will be will go into turbulence. So, we will look into what is turbulence, what are the fundamental processes in turbulence, and the reaction rate closure problem and basic modeling approaches. So, these will be will cover turbulence and turbulent combustion, and then we will cover turbulent non-premix and premix combustion, different kinds of flames, different turbulent non-premix flame, turbulent premix flames, turbulent flame speed and modeling. And then in the final part we will cover gas turbine combustors. How does for example, first we will study about atomization, ignition and combustion in swirling flows, and then what are the basic principles by which a gas turbine combustor is designed, and finally in module 12 the flame stabilizations in afterburners and scramjets. So, here we will talk about bluff body stabilized flames, some parts of combustion diagnostics, and we will look into flame blow off mechanism, and then we will go into scramjets. Now, one thing is that these, even though I have formulated in these different modules, these modules need not be in equal length. For example, in this you can see that in module 11 and 12 we will be talking about a lot. So, we can reduce these things, we can reduce the different we will be using we will be looking into different topics on in preference of their importance. Okay. So, some topics can be more important, some topics can be less important, and will that we will this is the introduction.